Welcome students. So we are going to discuss integration of rational functions by partial fractions. So what are rational functions? So the idea is we want to integrate px over qx where px and qx are polynomials. So these are what the rational functions are, a polynomial divided by another polynomial. Now we can restrict our attention to the following case. So if the degree of numerator is bigger than the degree of denominator, then we can do a long division so that px by qx is equal to qx, which is the quotient, plus rx divided by q of x, in which case the degree of r of x is less than the degree of q of x. For example, if the degree of numerator is say x cubed plus 1 and if the numerator is x cubed plus 1 and denominator is x squared plus 1, we can do a long division to write it as follows. So how long division look like? X cubed plus 1 upon x squared, so divided by x squared plus 1. So this goes x times, we get x cubed plus x. When you subtract, you get what? You get minus x plus 1. So you can write this as x plus minus x plus 1 divided by x squared plus 1. So the idea is that if the degree of numerator is bigger than the degree of denominator, we can always reduce it to a polynomial, right? A polynomial plus a function, a rational function again, where the degree of numerator is less than degree of denominator. So we want to restrict our case in the following. So we want to restrict ourselves because otherwise then you can integrate. If you write it in this format here, you can always integrate it as what? Integral of qx plus integral of this rational function. So our focus will be on solving the problem r of x divided by q of x. So we want to integrate r of x divided by q of x dx, where what? Where we have the numerator degree is less than degree of denominator. So those are the rational functions we'll concentrate on because they can all be reduced to a polynomial plus a rational function of this form. So for purpose of investigating how to integrate rational functions, we will focus on f of x, which is px over qx, where degree of px is less than degree of q of x. Again, because of this possibility of writing it as a polynomial plus another rational function with the said property. So now we want to, so now our goal is clear. So our goal is to integrate px over qx dx, where degree of p of x is less than degree of q of x. Now, there is a property of every polynomial over q. So if you take any polynomial over q, either it will split into product of, so it will split into product of linear factors and or it will have some irreducible quadratic factors. Now, what are irreducible quadratic factors? Irreducible quadratic factors are factors which cannot be reduced further. Okay. So for example, let's take this guy, x cubed plus 1. So x cubed plus 1. So this theorem is telling us that we can write it as either all linear factors or we can write it as product of linear factors and quadratic factor. So let's see. For example, in this case, we have x cubed plus 1 is x plus 1 times x squared minus x plus 1. So this is a linear factor. And if this is further reduced, so now we have to see whether this can be reduced as a linear factor, product of two linear factors, or we have to write it as irreducible quadratic. So for that, we have a very easy test. We look for the discriminant. which is b square minus 4ac for this guy. So b square minus 4ac for this quadratic polynomial is what? Is b is minus 1, 4 is, well, 4ac is going to be, a is 1 and c is 1. So what do we get? We get b square minus 4ac is going to be 1 minus 4 times 1, which is going to be minus 3. So now your b square minus 4ac is less than 0, so this cannot be factorized further. So this is the complete factorization of it over q. Let's look at another example. So suppose I have x cube uh, plus x square plus x plus 1. Yeah, so in this case you can see that this can be written as what? This can be written as, take x square common, you have x plus 1. I'll modify this slightly. I'll write it as this if you don't mind. I want to work with this example. So what do I get? I get minus 1 times x plus 1. So this is going to be x square minus 1 times x plus 1, which is going to be x minus 1 times x minus 1 times, sorry, x plus 1 plus x plus 1. So you saw that this polynomial of degree 3 factored as all linear factors. So that is the idea behind this theorem, that if you take a polynomial over Q, either all the factors are linear or there are some linear factors and some quadratic factors. Those quadratic factors cannot be split further, and hence they are the name irreducible quadratic factors. So those quadratics are irreducible. Okay. So what does this has to do with our integration techniques? So our strategy is as follows. We'll factor q of x into linear and quadratic factors. We will write f of x as sum of partial fractions, where either it's of form, each fraction is of form k times ax plus b to the power s, or if the denominator is irreducible quadratic factor, it will be ax squared plus bx plus c to the power t, and in the numerator we have lx plus m. Okay, and then we'll integrate each of these partial fractions. So each of these terms are called partial fractions. So let's look at few examples and then we'll revisit this theory. So here we have 4x squared minus 3x minus 4 upon x cubed plus x squared minus 2x. So first thing is we'll factorize the denominator. So our q of x in this case is x common, what is left in the bracket, x squared plus x minus 2. And this can be split further. This is not irreducible, right? Because this has factorization x plus 2 times x minus 1. Now numerator, look at the degree of numerator. Degree of numerator is less than degree of denominator. So we can write this as a by x plus b by x plus 2 plus c by x minus 1. So this is what the theory of partial fraction tells us. And why this is possible, you have to see basically this as a space spanned by this 1 over x, 1 upon x plus 2, and 1 upon x minus 1. Okay. So, well, the partial fraction theory tells us that there exists such a, b, and c, so that we can write this expression here, equals to these three expressions. Yeah. And each of these terms are called partial fractions because you're writing it as sum of fractions and they are partial fractions of the original one. So now we want to find out what our a, b, and c's are, right? Because you see, if you knew a, b, and c, which are constants, then integrating the right hand side is pretty straightforward. So let's embark on that. So we'll say, so If both sides are equal, we'll get x plus 2 times x minus 1 plus b times x. So I'm going to multiply this with, I'm going to make denominators same. Okay. So I get bx times x minus 1 plus cx into x plus 2 equals to 4x squared minus 3x minus 4 whole divided by x cubed plus x squared minus 2x, and then divided by these three things multiplied, and multiplying these three things is same as what, same as x cubed plus x squared minus 2x. So compare the numerators. So these things are true for all x. So we have 4x squared minus 3x minus 4 equals to a times x plus 2 x minus 1 plus b times x into x minus 1 plus cx into x plus 2. So this is true for all x. Now what we'll do is the following. We need to solve for a, b, and c. So what we can do is we can basically we can compare the coefficients. So we can multiply it out and then compare the coefficients. Okay. So that's one way. Other way is take x equals to 1. If you take x equals to 1, what will happen? So if you take limit as x goes to 1 on both sides, you will see on this side you'll get what? X equals to 1 would give me 4 minus 3 minus 4, and on the other side you will get what? You will get, this will go away, this will go away, you'll get what? C times 3. So this gives me minus 3 equals to 3c, which gives me c equals to minus 1. Same way, what do we get? Otherwise, we can, if we take x equals to 0, actually you are not putting x equals to 0, you're taking limit as x equals to 0 on both sides. So you get x equals to 0. On top, what do you get here? You will get minus 4. On this side, what will happen? This will become 0, this will become 0. So you get what? You get a times 2 times minus 1. So this implies a equals to, so we get 0, so minus 4. Here we get a times, this will become a equals to 2. Now similarly, if you have x equals to negative 2, if you take limit of x goes to negative 2, you will get minus, so you'll get 8. So 4 times 4, which is 16. 16 plus 6 minus 4 on one side. On the other side, you will get, this will go away. This will become 0. You will have b times minus 2 into minus 2 minus 1, which is minus 3. So here you get, so we get, this gives us, so 22 minus 4 is 18. You get 6b. Therefore, b equals to 3. And then when we put it back, therefore our integral, you see, this will reduce to a by x plus b by x plus 2 plus c by x plus x minus 1. So when I write it like that, I'll get my integral I becomes integral a by, this fraction reduces to these, sum of these three partial fractions. So a by x, which is going to be 2 by x, then b, which is 3 upon x plus 2, minus c, which is 1 upon x minus 1 dx. Now if you integrate this, you'll get what? 2 comes out, ln of absolute value of x, plus 3 comes out, ln of x plus 2, minus 1 comes out ln of x minus 1 plus c. So this is your method of integration by partial fractions. Okay, so that's the idea. Let's proceed on next problem. So we have x cubed minus 4x minus 1 dx upon x into x minus 1 cube. So in the bottom you have what? You have repeated linear factor. And also you should check that degree of p of x less than degree of q of x, so that we don't have to perform any long division. We can directly write it down as follows: x cubed minus 4x minus 1 x into x minus 1 cube equals to a by x plus what? Now you have repeated factors here, so you have x minus 1 cube, so you have to write x minus 1 square plus x minus 1 cube. And because this is linear, on top you will have b. Because it's a square of a linear, still linear, so we'll have c. And then here we'll have what? D. So now we need to find out a, b, and c. So let's multiply it out. So we have, this is going to be a times x minus 1 cube plus b times x into x minus 1 square plus c times x into x minus 1 plus d times x. And that has to be x cubed minus 4x minus 1. Okay. Now we need to find out a, b, c, and d, right? So what we'll do is we'll compare the coefficients. So how will we compare the coefficients? So first of all, start with the constant term. The constant term. So what is the constant term here? On this side, the constant term is minus 1. On the other side, how do you get the constant term? You'll get constant term with what? The constant term will be when x's are 0 really, right? So you will see that constant term is, you will get, right? I mean, if you have any polynomial, say suppose I expand this polynomial out, yeah, multiply it out. So you will get bunch of things, say bunch of powers of, you will get something with x cubed, something with x squared, something with x plus 1. And the easy way to get something with a constant, so this will be a constant, and the easy way to get this constant is to put x equals to 0. So let's just do that. So when you put x equals to 0 here, you will get minus 1 cube. This will become 0, 0, 0. So we get minus 1 cube times a is minus 1. So this gives you a equals to 1. So you got a directly like that. Now next term to discuss is the x term. So now what are the x terms? So here we'll get minus 4 on this side, right? We have minus 4. What about the other side? So to get other side, note that when you expand this, what is the constant, what is the x term you get here? The x term you will get is, so you will get, when you expand x minus 1 cube, you get x square. So what is the formula for x minus 1 cube? X minus 1 cube is x cube minus 3x square plus 3x minus 1, right? So if I use that, I can see that it will be minus 3a. So I'm looking for x term. So x will come once and this will be square. So it will be actually plus. So plus x term will be 3a from here. In this case, how can you get x term? It will be this guy multiplied by constant term here. What is the constant term here? It's 1. So you will get plus b. Here, the only way you can get x term is when you multiply it with the next one, which is going to be minus c, and here plus d. Okay, so we can't solve it yet, right? We only know basically x term. So let's look at the next term. What about x square term? So x square term. On this side you have 0, right? Because this side you have no x square term. So it will be 0 equals to, what do you get on this side? So you will get x square term by this part here, right? So we get minus 3a. Here you will get x square term when bx multiplied with minus 2x of x minus 1 square. So you'll get minus 2b. And here you will get x square when you multiply cx with this. So plus c equals to 0. So, and then the last one. So now from here, what about the last, which is x cubed term? So let's match x cubed term. X cubed term will be, here it is 1 on your left hand side. On your right hand side, you can get x cubed term from this part. So you get a, and then you get, here there is an x cubed term when you multiply bx with x squared. So plus b. There is no x cubed term here, right? Because whatever you do here, you will not get any x cubed term. So these are the system of equations you need to solve to find a, b, c, and d. So we have already have a with us. So this will give us b equals to 0, right? Because since a is 1, you get 1 equals to 1 plus 1 b. This gives me b equals to 0. Now take that, plug it back in this equation. Here. So this will give us 0 equals to minus 3 minus 0 plus c. So we get c equals to 3. So we got b equals to this, and what about d now? So let's see. This implies I have minus 4 equals to 3 times a, which is 1, plus b, which is 0, minus c, which is 3, plus d, which is going to be what we are looking for. So therefore d equals to negative 4. Okay. So these are the values we got now. Let's put it back. So we get our integral I. Let's call this integral I. The inside part splitted as partial fractions. So we have a over x. A is 1, so 1 over x. B over, which is 0 over x minus 1. So that will not participate in the integral. Plus c, which is 3 upon x minus 1 square, plus d, which is minus 4 upon x minus 1 cube dx. So this whole process was to write it as these partial fractions because each of them is easy to integrate. So what is the integral of first one? Ln of absolute value of x. This guy will be ignored. So here you will get plus, so this is a x to the power minus 2, which is going to be 3 times x to the power minus 1 divided by minus 1. Here you have 4 to the power, so we get 4 times x to the power minus 1, sorry, x minus 1 to the power minus 2 divided by minus 2 plus c. And if you want to write it in a slightly more organized way, this integral is going to be ln of absolute value of x minus 3 upon x minus 1 plus 2 upon x minus 1 squared plus a constant c. So this is how the integration by partial fraction works. Okay. So again, the choices of A, B, C, D has to be done. Right? Now note that instead of doing this, you could have multiplied the everything out here. So in this line, you could have multiplied everything out, but well, it's better to look at the coefficients and compare them. So let's move on to the next problem. So now let's look at the next problem. Again, before I apply the partial fractions, I need to see the degree of numerator is what? Degree 3 over degree 4. So no long division needed really to start with. So what is the factorization of denominator? Factorization of denominator is x square times x plus 1. Sorry, x square plus 1. This is what your denominator is. So we'll write the partial fraction now. So we have 5x cubed minus 3x squared plus 2x minus 1 divided by x to the 4 plus x squared. Now we have to write, so here we have x squared. So corresponding to x squared, we have to write x and then x squared. Now these are squares of linear term, right? After all, this is inside is a linear term. So we have a, we have b. Note that x square is actually x minus 0 square. So it's a square of a linear term. Now, for this x square plus 1 part, you have to write it as x square plus 1. Now note that this is irreducible. You can't break it further, right? So if you can't break it further, you have to write cx plus d. Yeah. So if you have an irreducible quadratic factor, the top part has to be a linear cx plus d. Now, why it has to be linear? That's the only way you can construct all kinds of combination and get a polynomial as general as this. So let's work this out now. So we need to find out A, B, C, and D. All right. So let's proceed on this. So we have 5x cubed minus 3x squared. So 5x cubed minus 3x squared plus 2x minus 1. And this is going to be cross multiply. So we have a times x into x squared plus 1 plus b times x squared plus 1 plus cx plus d times x squared. Okay. Now again we have to play the same game. Compare the terms. So let's see what is the constant term here. So on this side the constant term is minus 1. On this side, there is no constant term here because you have to, whatever you expand this part, you have to multiply by x. So there's no constant term here. In this part, you have a constant term, which is b. And in this part, there's no constant term because whatever you have to multiply by x squared. You won't get any constant term. So you got b equals to minus 1. Now let's compare coefficient of x. So let's see on the left hand side, what is the coefficient of x? We have 2. On the right hand side, how do we get coefficient of x? So there is 1 coming from here, which is a, right? Ax plus a. Here there will be no x term, so nothing here. In this part here, again, everything is getting multiplied by x squared. So there is no x term here as well. So comparing coefficient of x, we got a equals to 2. Now let's compare coefficient of x squared. On this side we have minus 3. On the other side, let's see. We don't get any coefficient of this from here, from the first part, because the only way to get x square would be, there's no way to get x square here. Now, on this part, you get b. And here you can get x by multiplying these two. So we get b plus d equals to 3. So you already know, so this will give me, if I combine it with b equals to -1, this gives me -3 equals to -1 plus d. So therefore d equals to -2. Now the last term to compare, coefficient of x cube. So we get coefficient of x cube is 5. On the other side, what do I get? Can I get x cube here? Yes, I multiply this with ax with x square, I get x cube. So a, there's no x cube coming from here. There is an x cube coming when I multiply these two things. So I get plus c. So I get 5a plus c equals to 5. A is 2, so this gives me c is 5 minus 2, which gives me 3. So now how will so I have done, we have solved for a, b, c, and d. So now our integral I, if I call this as integral I, our integral I will look like, I'm reading from this part here, this line. So we get I equals to integral a by x, which is 2 by x, plus b by x. So b is -1, so -1 by x square, plus cx, so 3x minus 2 by x squared plus 1. So this is the integral we want to integrate. Okay. So now the first part is going to be 2 ln of absolute value of x. What is the integral of minus x squared? Is going to be plus 1 by x. Yeah, you can use the power rule. Now for this guy, you need to break it into two parts again. So this is going to be integral of 3 times x upon x squared plus 1 dx minus 2 times integral of 1 upon x squared plus 1 dx. Now in this case, you can see what is integral. So let me work this on side. Integral of x upon x squared plus 1 dx. If you do the substitution, you will see that this is going to be 1 by 2 ln of x squared plus 1. So you will see that this is going to be 2 ln of absolute value of x plus 1 by x plus 3 by 2 times ln of x squared plus 1. I generally have absolute value sign, but I know that x squared plus 1 is positive. So I will avoid putting absolute value sign. And 2 times, what is the integral of this? This is tan inverse of x plus c. So this is the whole integral. So this is how the game works. Now let's move on to the next problem. So for the next problem, again, we have the following. We have constant over degree 5, so a quintic polynomial, so that's fine. So in this case, we can write as 1 upon x into, so we can apply the partial fraction right away without applying any long division. So again, we should write it as, so now for x term, it's a linear term. So we have a upon x. Now we have x squared plus 1 the whole square. So this should go as x squared plus 1 first, and then x squared plus 1 the whole square. Now note that x squared plus 1 is an irreducible term. So I should write on top here bx plus c, and then I have dx plus e. So we need to solve for A, B, C, and D, and that will help us to integrate this guy. So let's work it out. So we get this is going to be A times x squared plus 1 plus B times x into x squared plus 1 plus C, sorry, D, sorry, bx plus C times bx plus C times x into x squared plus 1. So this should have had square here, plus dx plus E times x, and this is equal to 1. Now we want to compare all the terms again. So we want to first compare the constant term. Now to compare the constant term, either see where you can get constants or just put x equals to 0. So when you get x equals to 0, he'll get A, everything else will be 0, right? So set x equals to 0, this will give us 1 equals to A. Now we want x cube, x square, x4 term. So let's first see that I'll work with x4 term. On this side, I get what is my x4 term? So I will get x4 term from here is going to be, on this side, the x4 term is 0. On the other side, I'll get A. Is there any x4 term here? And the answer is yes, when you multiply x square with x with bx. So you get plus b. Is there any x squared x4 term? No. So we get a plus b equals to 0, which gives me b equals to -1. Now what about x cube term? So we get, on this side, there's no x cube term, right? So we get 0 equals to, now let's see, where will we get x cube term? So here, when you expand this, it's x square plus x to the 4 plus 2x square on this part, right? So there's no x cube term. On this part, you get x cube when you multiply x with c with x square. That's the only way you can get x cube term. So you get c, and there's no x cube term on this side. So what do we get? We get 0 equals to c. Now what about x term? So let's see, there's no x term here. What about this guy? How can we get x term? We can get x term only when we multiply c with x with 1. So we get 0, x term is not there on this side, and we get c. And here, can we get an x term when we multiply e with x? So we'll get c plus e. So this gives me e is also 0, right? Now I missed x squared term. I should have taken that into consideration, but however, better late than never. Let's see. So there's no x squared term, so 0. What do I get here? If I look at x squared term, I can get 2x squared in this part here, right? So this gives me, if I expand this, I get 2x squared, right? So I get 2a. Can I get an x squared term here in this piece here? And the answer is yes. If I multiply b with x and 1, so I can get, the only way I can get x squared is multiply this guy with this guy with this guy, and that's the only way out. So what do I get? So this will give me plus b. And is there a way to get x squared here? Yes, when I multiply this x with this dx. So what will I get in that case? I get plus d. So from here, we can make out that, well, a is 1, b is -1. So I get 0 equals to 2 minus b plus d. So this will give me d equals to, we bring it on the other side, you get d equals to what? So d equals to -1. So we got all these terms now. So I can write my I is going to be integral a over x, so 1 over x, plus b, which is -1 times x over bx plus c. What is my c? So my c is 0, so I should write it as minus x over 1 plus dx plus e. What is my d? My d is -1. My so d is -1. And what do we have for e? E is 0. So we have x squared plus 1 the whole square dx. Now here we'll use substitution rule, right? Wow. And here also you'll use substitution rule. So please go ahead and integrate it. You will see that this is going to be ln of absolute value of x minus half ln of x squared plus 1. And here you will get, again by using substitution in this part, you'll get half x squared plus 1 plus c. So this is how the partial fraction works. So you see, you are able to integrate this complicated integral using this setup. All right, now let's move on to the next problem. So here, find the volume of the solid obtained by region R, revolving region R, which is this region here, which is shaded here for you, between the curves y equals to x minus 9, x squared minus 3x. And from the x-axis, so we are revolving it around y-axis, but this is our region, which is given in shaded part here, right? So this is our region. Yeah, there's no reason to recolor it, but let's just recolor it for the fun sake. So this is our region, and we want to basically find what is the volume of this region. Okay, so the easy way out to compute this would be using the method of cylindrical shells. So let's use the cylindrical shells to find out the volume in this case. So we will take one of these guys, one of these shells, and multiply. And so what is the volume by shell method? You have integral a to b 2 pi x f of x dx if you are rotating around y-axis, yeah, not around x equals to something, but around y-axis. So in this case, the limits of integration are from 1 to 2. That is already given to us. So volume is going to be integral 1 to 2 pi x, and f of x is given by x minus 9 upon x squared minus 3x. So this is our volume. V is going to be 2 pi can be taken out. X can be cancelled off. You have 1 to 2 x minus 9 upon x minus 3 dx. Now in this case, if you want to solve this, first notice that degree of denominator equals to degree of numerator. So we'll have to use long division first to simplify this, because we can't apply partial fractions right away. So when you apply long division, you get x minus 9 divided by x minus 3 goes 1 times. We have x minus 3, left is what? Minus 6. So we can write this as 2 pi integral 1 to 2 1 minus 6 upon x minus 3 dx. Yeah, you did not necessarily need to do the long division. You could have written it like this as well. You could have written this as and worked it out, but long division makes it clearer. And it's basically, it will work in all the cases. So we get 2 pi. Now integral of 1 is x, and integral of this is 6 ln of absolute value of x minus 3, 1 to 2. So when you substitute the upper limit, you will get 2 pi 2 minus 6 ln of 2 minus 1. So ln of absolute value of minus 2. Right? When you put 2, you get 2 minus, so sorry, 2 minus 3, which is minus 1, my bad. Minus, so let's put this in bracket. Minus, when you put 1, 1 minus 6 times ln of absolute value of 1 minus 3, which is minus 2. So ln of absolute value of minus 2. Now let's simplify this. So 2 pi 2, this will become 0, minus 1, minus of minus plus 6 ln 2. This is going to be 2 pi 1 plus 6 ln 2. So this is your integral. Okay. Now let's generalize this process completely. So again, we are going to go back and look how to go about it in generality. So suppose you're given an function f of x, which is px divided by q of x, where degree of p of x is less than q of x. So the numerator degree is less than degree of denominator. So step 1 is to always split qx into linear and irreducible quadratic factors. So you have, suppose q of x is a big polynomial and you have, these are the linear factors. The linear factors will also appear with some power. Yeah, the power could be 1, 2, 3, depends on your q of x. And then you have irreducible quadratic factors like that. Yeah. Now for each of this, say for this part only and this part, how will it look like? I will have, say suppose instead of a1x plus b1 to the power 3, suppose if I had that, then I will get this contribution of just this part will be a upon a1x plus b1 plus b upon a1x plus b1 square plus c upon a1x plus b1 cube. Yeah, so when it's degree 3. So if it is degree r1, what will be the factor, what will be the contribution for this part? The contribution for this part will be a1x plus b1 divided, over some, the numerator will be some constant. I'm choosing to call it as a11. Similarly, a1x plus b1 square here, keep on going until we reach what? r1. So we have a1x plus b1 r1. And we have some constants on top. Same thing will go for the next constant and all these. So for last one, for example, for each of these, for last one here, we have an x plus bn to the power rn. So same thing will happen here. An x plus b1, then we have an x plus bn square, and so on all the way until power rn. So these are for the repeated linear factors, right? Nobody is claiming that the factor has to be bigger than 1, but we are writing the absolute general case. Now, what about the irreducible part? So irreducible quadratic factor, suppose it comes with power s1, then you will have what? So this part with power 1, this part with power 2. I'll keep on going until you get power s1. And on top of irreducible, you always have a linear. So we have b11x plus c11, b12x plus c11, on 2, and so on and so forth. So you keep on doing this process, and then you integrate each part, and that's how you can integrate a general rational function using a method of partial fractions.